What if some of the most important parts of our universe are the things we cannot easily see? The darkness between stars, the light that has traveled for billions of years, the hidden forces shaping galaxies, and the strange ways time behaves near the most extreme objects in existence all reveal a universe far more connected than it first appears. In this journey through 100 sleepy wonders of our universe, we'll explore how stars are born, how planets wander through space, why black holes challenge our understanding of reality, and how entire galaxies are organized across unimaginable distances. Along the way, you'll discover patterns that link the smallest cosmic details to the largest structures ever observed. If you enjoy thoughtful science explorations like this, consider subscribing to Calm Science Lab. There is always another fascinating question waiting beyond the next horizon. Settle in for a quiet exploration of the cosmos, and begin with a simple question. Why does darkness reveal so much about the structure of the universe? 1. Why darkness reveals the universe's structure. Darkness often seems like an absence. In daily life, it is what remains when lights are switched off, when the sun slips below the horizon, or when clouds conceal the brightness of the sky. Yet in astronomy, darkness plays a very different role. It is not merely the background against which the universe appears. In many ways, darkness is one of the most important tools for understanding reality itself. Without it, much of the structure of the cosmos would remain hidden. The vast architecture of the universe becomes visible not despite darkness, but because of it. When people imagine the universe, they often picture countless stars scattered across space. The image is understandable. Stars are bright, easy to notice, and visually striking, yet stars represent only a small fraction of what exists. Most of the universe is not made of glowing objects. Most of it is dark. The spaces between stars stretch across immense distances. Galaxies are separated by expanses so large that human intuition struggles to grasp them. If every star suddenly vanished, much of the universe's underlying structure would still remain. The challenge would simply be finding a way to detect it. This raises an interesting question. How can darkness reveal anything at all? The answer begins with a simple observation. Human eyes notice contrast. A bright object against a bright background can be difficult to see. A bright object against darkness stands out immediately. The night sky demonstrates this principle every evening. During the day, stars remain overhead, but sunlight scattered through Earth's atmosphere overwhelms them. Only when darkness returns do the stars emerge. The darkness does not create the stars, it allows them to be seen. Astronomers rely on this principle constantly. Throughout history, every improvement in observing the universe has involved finding ways to reduce unwanted light. Ancient skywatchers traveled away from fires. Modern observatories are built far from cities. Space telescopes leave Earth's atmosphere entirely. In each case, the goal is similar. The darker the surroundings become, the more subtle structures emerge from the cosmic background. Consider the Milky Way. Under bright, urban skies, only a handful of stars may be visible. Travel to a remote desert or mountaintop, however, and a faint river of light stretches across the heavens. This glowing band is not a cloud. It is the combined light of billions of distant stars packed together within our galaxy. For countless generations, people gazed at this luminous pathway without fully understanding what it represented. Yet the darkness surrounding it provided a clue. The Milky Way appeared concentrated along a specific region of the sky rather than evenly distributed. That pattern hinted at a larger structure. Eventually, astronomers realized that our solar system resides inside a vast spiral galaxy. The bright band crossing the sky marks our view through the dense disk of stars that forms part of its shape. Darkness helped reveal this arrangement. By studying where light appeared and where it did not, researchers began mapping our position within a much larger system. Darkness reveals another important truth. Empty-looking regions are often not empty at all. Some of the most fascinating discoveries in astronomy emerged when scientists noticed areas where light seemed to be missing. Imagine looking at a field of stars and finding a strange dark patch. At first glance, it might appear to be a gap where no stars exist. Early observers sometimes interpreted such regions this way, but closer investigation revealed something unexpected. Many dark areas are actually enormous clouds of gas and dust, blocking light from behind them. These cosmic clouds can stretch for dozens or even hundreds of light years. They contain the raw materials from which future stars and planets may eventually form. Their presence becomes apparent precisely because they create darkness. Like a silhouette against a distant lamp, their outlines emerge by obscuring something brighter beyond them. In this way, darkness acts almost like a map, tracing structures that would otherwise remain invisible. One famous example is found within regions of active star formation. Dense clouds drift through space, absorbing visible light. To ordinary telescopes, these areas appear as dark lanes winding between brighter regions. Yet infrared instruments reveal something remarkable hidden inside. Within the darkness, new stars are being born. The apparent emptiness conceals extraordinary activity. Darkness, rather than indicating absence, marks the location of creation itself. The relationship between light and darkness becomes even more intriguing when astronomers study galaxies beyond our own. Viewed from a distance, many galaxies display elegant spiral arms curving outward from their centers. Bright stars outline these structures, but darkness often helps define them more clearly. Dust lanes snake through the glowing arms, emphasizing patterns that reveal how galaxies are organized. By examining these contrasts, scientists learn about motion, composition, and evolution across immense spans of time. As telescopes improved, astronomers began noticing an even larger pattern. Galaxies were not scattered randomly throughout space. Instead, they formed clusters, groups, and vast interconnected networks. Some regions contained enormous concentrations of galaxies. Others appeared surprisingly sparse. When researchers mapped these distributions on cosmic scales, an extraordinary picture emerged. The universe resembles a vast web. This cosmic web consists of immense filaments stretching across hundreds of millions of light years. Galaxies gather along these strands, while enormous voids occupy the spaces between them. The resulting structure is among the largest known features in existence. Remarkably, much of it became apparent through the study of where galaxies were absent as much as where they were present. Darkness outlined the shape of the universe itself, and as astronomers continued exploring these immense patterns, they encountered an even deeper mystery, one suggesting that the darkness filling the cosmos may not simply reveal structure, but may actually help create it. 2. Ancient starlight crossing vast cosmic distances. The idea that darkness may help shape the universe naturally leads to another remarkable realization. Every time astronomers observe distant objects, they are not simply looking across space, they are also looking backward through time. Light does not travel instantly. It moves at an extraordinary speed, faster than anything else known in nature. Yet the universe is so vast that even light requires significant time to cross it. This simple fact transforms the night sky into a record of history. Every beam of starlight carries information from a different moment in the past, preserved across immense distances before finally reaching Earth. When we look at the sun, we see it not as it exists at that exact instant, but as it appeared roughly 8 minutes earlier. Sunlight needs about 8 minutes to travel from the solar surface to our planet. The delay is small enough that it rarely matters in daily life, yet it reveals an important principle. Observation always involves travel time. The farther away an object is, the older the image we receive. The nearest stars beyond the sun are several light years away. A light year is not a measure of time but of distance. It represents how far light can travel in 1 year, covering nearly 6 trillion miles, or about 9.46 trillion kilometers. When astronomers observe a star 4 light years away, they are seeing light that began its journey 4 years ago. The star may have changed in subtle ways since then, but the information reaching Earth still belongs to that earlier moment. As distances increase, the effect becomes more dramatic. Many stars visible in the night sky are hundreds or even thousands of light-years away. Some of the light entering a telescope tonight may have departed its source long before modern technology existed. Certain photons began their journeys before the invention of the printing press. Others left their stars when ancient civilizations were still building monuments whose ruins remain today. The sky becomes a collection of overlapping eras, each arriving simultaneously despite originating from different periods of history. This perspective changes how we think about the universe. On Earth, people experience time together. Although time zones create differences in local clocks, everyone shares the same general moment. Across cosmic distances, however, there is no single visual present. Every direction contains a different chapter of the universe's story. Looking farther away means looking deeper into the past. Distance functions almost like a time machine built into the structure of reality. The realization emerged gradually. For much of human history, stars appeared fixed and eternal. Their immense distances were difficult to imagine because there was no practical way to measure them. Even after astronomers accepted that stars were distant suns, the scale remained astonishing. The nearest stars were so far away that their positions shifted only slightly as Earth moved around the Sun. Detecting those tiny changes required extremely careful observations. As measurements improved, the universe expanded in human understanding. Distances that once seemed enormous became relatively local. Our galaxy alone contains hundreds of billions of stars spread across a disk roughly 100,000 light-years wide. Light crossing from one side of the Milky Way to the other would require far longer than the entire span of recorded human history. Suddenly, the cosmos appeared not merely large, but almost unimaginably vast. Beyond the Milky Way lie countless other galaxies. Each contains its own stars, planets, clouds, and history. The nearest large galactic neighbor, the Andromeda Galaxy, is more than 2 million light-years away. The light reaching Earth from Andromeda tonight began traveling toward us long before the earliest members of our species learned to use written language. What appears as a faint patch of light in the sky is actually a message preserved across millions of years. As telescopes became more powerful, astronomers pushed their observations farther into space. They discovered galaxies so distant that their light had traveled billions of years before arriving. Some of these galaxies are seen as they existed when the universe was only a fraction of its current age. Their stars were younger, their structures were less developed, their environments differed significantly from those observed nearby. By comparing galaxies at different distances, researchers effectively compare different stages of cosmic history. This method provides a unique advantage. Historians studying human civilizations often rely on incomplete records. Ancient documents decay, structures collapse, evidence disappears. The universe preserves its own archive in a different way. Light itself becomes the record. Every photon carries information about the conditions present when it was emitted. The farther astronomers look, the older the record becomes. Ancient starlight contains clues about temperature, composition, motion, and age. When light passes through a prism or a spectrograph, it separates into different wavelengths. Hidden within those patterns are signatures produced by specific elements. Hydrogen leaves one set of marks, helium leaves another. Oxygen, carbon, iron, and many other elements each create distinctive fingerprints. By studying these signatures, astronomers can determine what distant stars and galaxies contain without ever physically visiting them. This achievement is one of science's quiet triumphs. A beam of light crossing billions of years can reveal the chemistry of an object unimaginably far away. It allows researchers to reconstruct environments that no spacecraft could currently reach. The universe communicates through light, and astronomy is largely the art of learning how to read those messages. Yet, ancient starlight reveals more than composition. It also tells a story about motion. As the universe expands, space itself stretches. Light traveling across that expanding space experiences a gradual change. Its wavelengths lengthen, shifting toward the red end of the spectrum. This phenomenon, known as redshift, serves as a measure of cosmic distance and history. The greater the redshift, the farther the light has traveled, and the earlier the era from which it originated. Through these measurements, astronomers discovered that the universe has been expanding for billions of years. Galaxies are not stationary islands suspended in an eternal void. Instead, the cosmos itself evolves. Ancient light preserves evidence of that transformation. It shows how galaxies formed, how stars accumulated, and how cosmic structures gradually emerged from simpler beginnings. Perhaps the most extraordinary example of ancient light comes from a faint glow that fills all of space. This radiation does not originate from a single star or galaxy. It comes from a much earlier epoch, when the universe itself was young, hot, and dense. After traveling for more than 13 billion years, that ancient signal still reaches Earth today. It represents one of the oldest forms of light humans can observe. And within that primordial glow lies the next chapter of our exploration, revealing how the first structures began to emerge from a universe that was once astonishingly simple. 3. Silent birthplaces where new suns emerge. Long before planets formed, before oceans existed, and before any living creature could look upward and wonder about the sky, the universe had to solve a fundamental problem. It needed a way to create stars. Every star that shines today, from the smallest red dwarf to the brightest giant, began within environments that are surprisingly quiet and hidden. These places are not marked by visible drama when viewed across cosmic distances. Instead, they often appear as dark clouds drifting through space, subtle regions where gravity patiently gathers material over spans of time that far exceed a human lifetime. Within these silent birthplaces, new suns gradually emerge. The process begins inside enormous molecular clouds. These vast collections of gas and dust are among the coldest places in the galaxy. Temperatures can fall so low that atoms move only sluggishly compared to the energetic environments found inside stars. Yet these cold conditions are important. Heat creates pressure that pushes outward, resisting collapse. In colder regions, gravity gains an advantage. Slowly, almost imperceptibly, matter begins gathering into denser pockets. A molecular cloud may stretch across dozens or even hundreds of light years. From a distance, it can appear as a dark obstruction against richer fields of starlight. For centuries, observers often saw these regions as empty gaps. Modern instruments revealed something different. The darkness comes not from absence, but from abundance. Dust grains scattered throughout the cloud absorb and block visible light. Hidden behind that veil lies the raw material for future generations of stars. Within these clouds, small irregularities become important. No cloud is perfectly uniform. Some regions contain slightly more mass than others. Gravity amplifies those differences. Areas that are already somewhat denser attract additional material. As more gas accumulates, gravitational pull strengthens further. A gradual cycle begins, one that can continue for millions of years. What starts as a subtle concentration eventually becomes a distinct collapsing core. At first, the changes are difficult to detect. The cloud remains cold and dark. Yet deep inside, the density steadily increases. Particles collide more frequently. Material falls inward. Gravity converts potential energy into heat. Temperatures begin rising. The core becomes warmer than its surroundings, though it may still remain hidden from visible light telescopes. Infrared instruments, however, can detect the faint warmth emerging from these developing structures. The image of star birth often differs from reality. It is tempting to imagine a sudden ignition, as though a cosmic switch is flipped and a star instantly appears. Nature works more gradually. A forming star spends a long period as a protostar, a young object still gathering material from its surroundings. Gas spirals inward through rotating disks. Magnetic fields influence the flow. Powerful jets can emerge from the poles, carrying energy outward while the growing object continues accumulating mass. These jets are among the earliest visible signs that a new star is taking shape. They can extend for light years into surrounding space, interacting with nearby gas and dust. Although impressive, they represent only one part of a much larger process. Most of the action remains hidden within dense clouds where gravity continues its patient work. Eventually, the central temperature climbs high enough for something remarkable to occur. Hydrogen nuclei begin fusing together. This process releases enormous amounts of energy. For the first time, the object generates its own lasting source of power. A true star is born. The pressure created by fusion balances gravity's inward pull, establishing a long-lasting equilibrium that may endure for billions of years. The birth of a star is not merely the creation of a luminous object. It also transforms its environment. Radiation streams outward. Stellar winds push against surrounding gas. Nearby regions may be compressed, potentially triggering the formation of additional stars. In this way, one generation can influence the next. Molecular clouds become dynamic ecosystems where creation spreads through interconnected processes. Many stars do not form alone. Large clouds often produce entire clusters. Hundreds or thousands of young stars can emerge within the same region, each following a slightly different path depending on its mass and local conditions. Some become small, long-lived stars that may shine for trillions of years. Others grow massive and bright, burning their fuel rapidly before ending their lives in spectacular ways. The diversity observed across the galaxy begins with subtle differences present during formation. Among the most fascinating aspects of these stellar nurseries is the role of dust. Dust particles constitute only a small fraction of a cloud's total mass, yet they profoundly influence what happens inside. They help cool the gas, allowing collapse to continue. They also provide building materials for future planetary systems. The same dust that obscures newborn stars may eventually contribute to rocky worlds orbiting them. Around many young stars, rotating disks of material remain after formation. Within these disks, tiny particles collide and stick together. Over immense periods, larger structures emerge. Pebbles become larger aggregates. Larger aggregates become planetesimals. Some eventually grow into planets. In this sense, the birth of a star often marks the beginning of another story. The processes that create sunlight and the processes that create worlds are deeply connected. Observations of stellar nurseries throughout the Milky Way reveal an astonishing variety of environments. Some regions contain only a few forming stars. Others produce thousands. Certain clouds are relatively calm, others are shaped by nearby massive stars, whose radiation carves cavities through surrounding gas. Despite these differences, common patterns appear again and again. Gravity gathers material, collapse generates heat, fusion begins. A new source of light enters the galaxy. What makes these birthplaces especially remarkable is their continuity across cosmic history. The same fundamental processes that operate today likely occurred billions of years ago. Ancient galaxies formed stars. Present-day galaxies form stars. Future galaxies will continue doing so as long as sufficient gas remains available. The universe repeatedly transforms diffuse matter into concentrated sources of energy, renewing its stellar population across vast spans of time. Yet not all stars are alike. Some emerge modestly, possessing only a fraction of the Sun's mass. Others become giants capable of reshaping entire regions of space. Their differing lives influence the chemistry, structure, and future evolution of galaxies. To understand how the universe developed its complexity, it becomes necessary to follow these stars beyond their birthplaces and explore the remarkable variety of worlds and systems that gather around them as they journey through the cosmos. 4. Planetary wanderers drifting through celestial seas. Once a star is born, the story of its surroundings is only beginning. The clouds and disks that helped create the star do not simply disappear. Much of the remaining material continues orbiting, circling through space in intricate patterns shaped by gravity. Over time, some of this matter gathers into planets, moons, asteroids, and comets. What emerges is not a static arrangement, but a dynamic system of wanderers, each following paths that may persist for billions of years. These planetary travelers drift through the vastness of space, like ships crossing an immense and largely invisible ocean. For most of human history, planets occupied a special place in the sky. Unlike stars, which appeared fixed relative to one another, planets moved. Night after night, careful observers noticed these bright points slowly changing position against the stellar background. The ancient Greeks called them wanderers, a term that reflected their unusual behavior. Although the reasons behind their motion remained mysterious for centuries, the name captured an important truth. Planets are travelers. The motions that once seemed puzzling eventually became understandable through the laws of gravity. A planet is constantly falling toward its star, yet it also possesses sideways motion. These two tendencies balance one another. The result is an orbit, a continuous journey around a central source of gravity. The planet never reaches the star because its forward motion carries it onward. It never escapes because gravity continually redirects its path. This elegant balance creates the stable systems observed throughout the universe. Our own solar system offers a familiar example. The planets travel around the Sun at different distances and speeds. Mercury completes an orbit in only a few months, while Neptune requires more than a century. Each world follows its own route, yet together they form a coherent gravitational community. Their motions are not random. They are connected through a complex web of interactions that has evolved over billions of years. What is remarkable is that such systems appear to be common. For much of modern astronomy, scientists knew of only one planetary system, our own. The existence of planets around other stars seemed likely, but evidence remained elusive. Stars are bright, planets are comparatively faint. Detecting distant worlds proved extremely difficult. Yet as observational techniques improved, astronomers began uncovering an astonishing reality. Planets are everywhere. Today, thousands of exoplanets have been identified orbiting distant stars. Some resemble familiar worlds, others challenge expectations entirely. Certain planets are larger than Jupiter and orbit extremely close to their stars, completing a year in only a few days. Some appear covered by deep global oceans. Others may possess atmospheres rich in exotic compounds. The diversity is far greater than many researchers once imagined. Each discovery expands the sense of what a planetary system can be. The solar system, once considered a template, now appears as only one example among countless possibilities. Nature does not follow a single design. Instead, it explores a vast range of outcomes shaped by local conditions, available materials, and gravitational history. One reason for this diversity lies in the chaotic nature of planetary formation. Young systems are crowded places. Newly formed planets interact with surrounding gas and with one another. These interactions can alter orbits dramatically. Some planets migrate inward toward their stars, others move outward. Certain worlds may experience close encounters that send them onto highly elongated paths. In extreme cases, planets can be ejected entirely. The existence of such ejected planets reveals one of the universe's quieter wonders. Not every planet remains attached to a star. Some travel through interstellar space alone. These free-floating worlds drift between stellar systems, wandering through the darkness without a permanent sun. They may have originated within ordinary planetary systems before gravitational interactions expelled them into the wider galaxy. The idea of a rogue planet crossing the depths of interstellar space carries a certain fascination. Imagine a world moving through near-total darkness, illuminated only by distant stars. Its surface conditions would depend on many factors. Internal heat generated by radioactive decay might persist for billions of years. Thick atmospheres could trap warmth. Subsurface oceans might remain liquid beneath layers of ice. Although such environments would differ greatly from Earth, they remind us that planetary existence is not limited to familiar circumstances. Even planets that remain within stellar systems are not motionless destinations. They participate in ongoing gravitational relationships. Moons orbit planets, planets orbit stars. Stars themselves orbit the centers of galaxies. Entire solar systems travel through the Milky Way at tremendous speeds. The sense of stability experienced on Earth arises partly because these motions occur smoothly and predictably over long timescales. Consider the Earth itself. Every second, our planet moves through space at remarkable velocity. It rotates on its axis, circles the Sun, and accompanies the Sun on its journey around the galactic center. Yet these motions are so consistent that they become invisible to everyday experience. Stability emerges not from stillness, but from reliable movement. This principle appears throughout the cosmos. Order often arises from motion rather than despite it. Planetary systems remain stable because countless gravitational influences balance one another across vast spans of time. Small changes can accumulate, yet the overall structure often persists for billions of years. Such longevity allows planets to develop complex histories of their own. Some worlds experience intense volcanic activity driven by internal heat. Others become frozen landscapes beneath distant suns. Certain planets possess rings composed of countless particles orbiting in coordinated paths. Some host multiple moons engaged in delicate gravitational dances. Every planetary system represents a unique outcome of cosmic evolution, shaped by conditions present during its formation and modified by events that followed. The study of these wandering worlds has also transformed humanity's perspective. For centuries, Earth seemed exceptional simply because it was the only known planet capable of supporting life. The discovery of thousands of other worlds does not diminish Earth's significance, but it broadens the context. Planets are not rare curiosities. They are natural products of star formation, appearing across the galaxy in extraordinary variety. As astronomers continue refining their instruments, they move closer to identifying worlds that resemble Earth more closely. They analyze atmospheres, measure temperatures, and search for subtle signs of chemical activity. Each new observation contributes to a larger question about the prevalence of habitable environments throughout the universe. Yet planets are only one part of these intricate systems. Around many of them travel smaller companions whose histories are equally fascinating. These natural satellites have been shaped by gravity, collisions, and time, preserving clues about planetary evolution and revealing another layer of structure hidden within the celestial seas. 5. Moons shaped by gravity's gentle sculpting. Among the countless objects that travel through the universe, moons occupy a particularly intriguing place. They are neither stars nor planets, yet they often play important roles in shaping the systems around them. Some are large enough to rival planets in size, others are little more than irregular fragments of rock captured by gravity long ago. Together they reveal how subtle forces, acting patiently across immense spans of time, can sculpt worlds into forms that are both diverse and surprisingly complex. The moon that circles Earth is so familiar that it can be easy to overlook its significance. It has accompanied human history from the beginning, influencing calendars, myths, navigation, and scientific inquiry. Yet from an astronomical perspective, Earth's moon is remarkable for another reason. Compared with its host planet, it is unusually large. This relationship creates gravitational effects that extend far beyond the beautiful sight of moonlight reflected across a nighttime landscape. Gravity between Earth and the moon generates tides. As the moon pulls on our planet, oceans respond by forming broad bulges that slowly move around the globe. The process appears gentle in daily life, but over millions and billions of years, these interactions accumulate meaningful consequences. Tidal forces gradually slow Earth's rotation. Long ago, a day on Earth was significantly shorter than the 24 hours familiar today. The moon's persistent gravitational influence has helped reshape the rhythm of our planet over geological time. At the same time, Earth's rotation transfers a small amount of energy back to the moon. As a result, the moon slowly drifts farther away. The change is extremely small from year to year, measurable only with precise instruments, yet it illustrates a broader truth. Planetary systems are not frozen arrangements. They evolve continuously through countless subtle exchanges of energy and momentum. This process of gravitational sculpting occurs throughout the solar system. moons and planets influence one another in ways that may seem minor over a human lifetime but become transformative over cosmic timescales. A moon's orbit may gradually change, internal heating may increase or decrease. Entire landscapes can emerge from interactions that operate almost invisibly from one century to the next. One of the most fascinating examples is found around Jupiter. The giant planet hosts dozens of moons, each possessing its own distinct character. Among them is Io, a world that appears unlike anything on Earth. Its surface is covered with active volcanoes, making it the most volcanically active object known in the solar system. At first glance, such intense activity might seem surprising for a moon. The explanation lies in gravity. Io follows an orbit influenced not only by Jupiter but also by neighboring moons. These competing gravitational pulls continually stretch and compress its interior. The process generates heat through friction, much as bending a piece of metal repeatedly can warm it. Deep inside Io, tidal heating fuels extensive volcanic activity. Here, gravity acts not as a destructive force, but as an engine, transforming orbital motion into geological energy. Nearby lies Europa, another moon shaped by similar influences, yet displaying a very different outcome. Beneath its icy surface, scientists believe a vast ocean may exist. Although Europa receives little warmth from the distant sun, tidal interactions generate enough internal heat to help maintain liquid water below the ice. This possibility has made Europa one of the most intriguing locations in the search for environments that could potentially support life. The contrast between Io and Europa demonstrates how small differences in conditions can lead to dramatically different worlds. Both moons orbit the same planet. Both experience tidal forces, yet one becomes a realm of volcanoes, while the other may conceal a deep global ocean. Gravity provides the common influence, but local circumstances shape the final result. Saturn offers another collection of remarkable moons. Among them is Titan, a world wrapped in a dense atmosphere richer and thicker than that of many planets. Rivers, lakes, and rainfall exist there, though not in forms familiar on Earth. Instead of water, Titan's surface features liquid methane and ethane. The processes resemble aspects of Earth's weather system while operating with entirely different materials. Titan demonstrates that planetary-style complexity is not limited to planets themselves. Enceladus, another moon of Saturn, presents yet another surprise. Despite its relatively modest size, it releases towering plumes of water vapor and ice particles from fractures near its south pole. Observations suggest the existence of liquid water beneath its frozen exterior. Here again, tidal forces appear to play a critical role, providing internal heat that sustains activity far below the surface. These discoveries have transformed scientific understanding of moons. They were once viewed largely as secondary objects, interesting companions to larger planets but not major destinations for investigation. Modern exploration reveals something far richer. Moons can possess atmospheres, oceans, weather systems, geological activity, and complex internal structures. Some may even offer environments where the basic ingredients for life are present. The origins of moons are as varied as their characteristics. Some likely formed alongside their host planets from the same disks of material that surrounded young worlds. Others may have originated elsewhere before being captured by gravity. Certain moons appear to be products of ancient collisions. Earth's moon itself is thought to have formed after a massive impact early in our planet's history, when debris from a colossal collision eventually gathered into a single orbiting body. These different origins help explain the diversity observed today. Each moon carries evidence of the processes that created it. Its composition, orbit, and structure preserve clues about events that occurred billions of years ago. In this sense, moons function as historical records. They retain information about planetary formation, migration, and evolution that might otherwise have been lost. The influence of moons extends beyond their own surfaces. Large moons can stabilize planetary rotation, affecting long-term climate patterns. Groups of moons can interact gravitationally, maintaining orbital resonances that persist across immense periods. Ring systems may owe part of their structure to the presence of nearby satellites. Throughout the solar system, moons participate in networks of relationships that shape larger environments. When viewed collectively, these worlds reveal an important lesson about the universe. Complexity often emerges from simple forces acting repeatedly over long durations. Gravity requires no elaborate mechanism. It merely attracts mass toward mass. Yet through countless interactions, it creates tides, generates heat, shapes orbits, and influences the development of entire planetary systems. What appears gentle on short timescales becomes profoundly creative when given enough time. And while moons preserve many stories of planetary history, they are not the only objects carrying ancient records. Beyond the major planets and their companions travel smaller wanderers, icy, rocky remnants that have remained largely unchanged since the earliest days of the solar system. These travelers preserve memories from a time before planets fully formed, offering rare glimpses into the conditions that existed near the beginning of our cosmic neighborhood. Among the countless objects that travel through the universe, moons occupy a particularly intriguing place. They are neither stars nor planets, yet they often play important roles in shaping the systems around them. Some are large enough to rival planets in size, others are little more than irregular fragments of rock captured by gravity long ago. Together, they reveal how subtle forces, acting patiently across immense spans of time, can sculpt worlds into forms that are both diverse and surprisingly complex. The moon that circles Earth is so familiar that it can be easy to overlook its significance. It has accompanied human history from the beginning, influencing calendars, myths, navigation, and scientific inquiry. Yet from an astronomical perspective, Earth's moon is remarkable for another reason. Compared with its host planet, it is unusually large. This relationship creates gravitational effects that extend far beyond the beautiful sight of moonlight reflected across a nighttime landscape. Gravity between Earth and the moon generates tides. As the moon pulls on our planet, oceans respond by forming broad bulges that slowly move around the globe. The process appears gentle in daily life, but over millions and billions of years, these interactions accumulate meaningful consequences. Tidal forces gradually slow Earth's rotation. Long ago, a day on Earth was significantly shorter than the 24 hours familiar today. The moon's persistent gravitational influence has helped reshape the rhythm of our planet over geological time. At the same time, Earth's rotation transfers a small amount of energy back to the moon. As a result, the moon slowly drifts farther away. The change is extremely small from year to year, measurable only with precise instruments, yet it illustrates a broader truth. Planetary systems are not frozen arrangements. They evolve continuously through countless subtle exchanges of energy and momentum. This process of gravitational sculpting occurs throughout the solar system. Moons and planets influence one another in ways that may seem minor over a human lifetime, but become transformative over cosmic timescales. A moon's orbit may gradually change, internal heating may increase or decrease. Entire landscapes can emerge from interactions that operate almost invisibly from one century to the next. One of the most fascinating examples is found around Jupiter. The giant planet hosts dozens of moons, each possessing its own distinct character. Among them is Io, a world that appears unlike anything on Earth. Its surface is covered with active volcanoes, making it the most volcanically active object known in the solar system. At first glance, such intense activity might seem surprising for a moon. The explanation lies in gravity. Io follows an orbit influenced not only by Jupiter, but also by neighboring moons. These competing gravitational pulls continually stretch and compress its interior. The process generates heat through friction, much as bending a piece of metal repeatedly can warm it. Deep inside Io, tidal heating fuels extensive volcanic activity. Here, gravity acts not as a destructive force, but as an engine, transforming orbital motion into geological energy. Nearby lies Europa, another moon shaped by similar influences yet displaying a very different outcome. Beneath its icy surface, scientists believe a vast ocean may exist. Although Europa receives little warmth from the distant sun, tidal interactions generate enough internal heat to help maintain liquid water below the ice. This possibility has made Europa one of the most intriguing locations in the search for environments that could potentially support life. The contrast between Io and Europa demonstrates how small differences in conditions can lead to dramatically different worlds. Both moons orbit the same planet. Both experience tidal forces, yet one becomes a realm of volcanoes while the other may conceal a deep global ocean. Gravity provides the common influence, but local circumstances shape the final result. Saturn offers another collection of remarkable moons. Among them is Titan, a world wrapped in a dense atmosphere richer and thicker than that of many planets. Rivers, lakes, and rainfall exist there, though not in forms familiar on Earth. Instead of water, Titan's surface features liquid methane and ethane. The processes resemble aspects of Earth's weather system while operating with entirely different materials. Titan demonstrates that planetary-style complexity is not limited to planets themselves. Enceladus, another moon of Saturn, presents yet another surprise. Despite its relatively modest size, it releases towering plumes of water vapor and ice particles from fractures near its south pole. Observations suggest the existence of liquid water beneath its frozen exterior. Here again, tidal forces appear to play a critical role, providing internal heat that sustains activity far below the surface. These discoveries have transformed scientific understanding of moons. They were once viewed largely as secondary objects, interesting companions to larger planets, but not major destinations for investigation. Modern exploration reveals something far richer. Moons can possess atmospheres, oceans, weather systems, geological activity, and complex internal structures. Some may even offer environments where the basic ingredients for life are present. The origins of moons are as varied as their characteristics. Some likely formed alongside their host planets from the same disks of material that surrounded young worlds. Others may have originated elsewhere before being captured by gravity. Certain moons appear to be products of ancient collisions. Earth's moon itself is thought to have formed after a massive impact early in our planet's history, when debris from a colossal collision eventually gathered into a single orbiting body. These different origins help explain the diversity observed today. Each moon carries evidence of the processes that created it. Its composition, orbit, and structure preserve clues about events that occurred billions of years ago. In this sense, moons function as historical records. They retain information about planetary formation, migration, and evolution that might otherwise have been lost. The influence of moons extends beyond their own surfaces. Large moons can stabilize planetary rotation, affecting long-term climate patterns. Groups of moons can interact gravitationally, maintaining orbital resonances that persist across immense periods. Ring systems may owe part of their structure to the presence of nearby satellites. Throughout the solar system, moons participate in networks of relationships that shape larger environments. When viewed collectively, these worlds reveal an important lesson about the universe. Complexity often emerges from simple forces acting repeatedly over long durations. Gravity requires no elaborate mechanism. It merely attracts mass toward mass. Yet through countless interactions, it creates tides, generates heat, shapes orbits, and influences the development of entire planetary systems. What appears gentle on short timescales becomes profoundly creative when given enough time. And while moons preserve many stories of planetary history, they are not the only objects carrying ancient records. Beyond the major planets and their companions travel smaller wanderers, icy, rocky remnants that have remained largely unchanged since the earliest days of the solar system. These travelers preserve memories from a time before planets fully formed, offering rare glimpses into the conditions that existed near the beginning of our cosmic neighborhood. 6. Comets preserving memories of early creation. If planets and moons are the great structures of a solar system, comets are among its oldest surviving archives. They are often described as visitors, appearing unexpectedly in the night sky before fading back into darkness, yet their true significance extends far beyond their visual beauty. Comets are time capsules from an era that existed before the planets reached their modern forms. Preserved in the cold outer reaches of the solar system, They carry materials that have remained largely unchanged for billions of years. By studying them, astronomers gain access to some of the earliest chapters in the story of cosmic creation. The modern solar system appears stable and organized. Planets follow established orbits. Moons circle their hosts. Asteroids occupy familiar regions. It is easy to imagine that things have always existed this way. In reality, the early solar system was a far more chaotic environment. Roughly 4.6 billion years ago, it began as a rotating cloud of gas and dust. Gravity gradually concentrated this material, forming the young sun at the center, while countless smaller particles collided and combined throughout the surrounding disk. Most of the material in that disk eventually became part of larger bodies. Some formed planets. Others contributed to moons, asteroids, and smaller structures. Yet not everything was incorporated into these growing worlds. Significant amounts of leftover material remained in distant regions where temperatures were extremely low. There, far from the warmth of the sun, primitive objects survived with relatively little alteration. Many of those objects became comets. Because they formed in such cold environments, comets contain large quantities of ice mixed with dust and rocky particles. Water ice is common, but comets also preserve frozen carbon dioxide, methane, ammonia, and other compounds. These substances were present during the solar system's earliest stages. Locked away in deep cold, they endured while planets underwent dramatic changes involving impacts, volcanism, and internal restructuring. For this reason, comets are often compared to preserved historical documents. A document written centuries ago may reveal details about a culture long vanished. Similarly, a comet can provide information about conditions that existed before Earth had oceans, before the Moon settled into its present orbit, and before the planets completed their formation. Each comet carries traces of a distant past that would otherwise be difficult to reconstruct. Most comets spend the majority of their existence far from the inner solar system. Two major reservoirs supply these icy wanderers. One is the Kuiper Belt, a broad region beyond Neptune populated by countless frozen objects. The other is the Oort cloud, a vast spherical collection of icy bodies extending far beyond the planetary region. The Oort cloud is so distant that its outer edge may lie nearly halfway to the nearest stars. Within these remote regions, comets can remain largely unchanged for immense spans of time. Darkness dominates their surroundings. Sunlight is weak. Temperatures are extremely low. A comet may spend millions or even billions of years drifting quietly through these distant reaches before a gravitational disturbance alters its path and sends it inward toward the sun. When this happens, one of the most recognizable spectacles in astronomy begins to unfold. As a comet approaches the inner solar system, increasing warmth causes some of its frozen materials to transform directly into gas. This process releases dust and vapor from the nucleus, creating a diffuse cloud known as a coma. Solar radiation and the solar wind then push material away from the comet, producing its famous tails. Interestingly, a comet's tail does not trail behind it in the way many people imagine. Instead, the tail points generally away from the sun. As the comet moves through space, its tail continually responds to solar influences. This means a comet can sometimes appear to travel with its tail leading or positioned at unusual angles relative to its direction of motion. The visual appearance of a comet reflects physical processes occurring on a small, icy body exposed to increasing sunlight. What seems like a graceful celestial display is actually evidence of ancient material being released into space. Every glowing tail contains particles that may have remained trapped since the earliest stages of solar system formation. For scientists, this makes comets extraordinarily valuable. Space missions have approached and studied them directly, revealing surfaces far more complex than once expected. Rather than smooth snowballs, many comets possess rugged terrains, cliffs, fractures, and irregular shapes. Their dark surfaces often reflect only a small fraction of incoming sunlight, making them surprisingly black compared with fresh ice on Earth. One of the most important discoveries from comet research involves organic molecules. Comets contain carbon-rich compounds that are relevant to the chemistry of life. This finding has encouraged scientists to consider whether comets may have contributed important ingredients to young planets. During the early history of the solar system, impacts were common. Comets striking Earth could have delivered water and organic materials, helping shape conditions that later allowed life to emerge. This possibility remains an active area of investigation. The exact contributions of comets are still being studied, but the idea highlights an intriguing connection. Objects formed in distant frozen regions may have influenced developments on worlds much closer to the Sun. The story of life's ingredients may not be confined to a single location, but linked to processes occurring across the entire solar system. Comets also reveal how interconnected celestial systems can be. Their paths are shaped by gravity from planets, stars, and even the broader galactic environment. A passing star may slightly disturb distant icy bodies in the Oort cloud. Millions of years later, one of those objects might enter the inner solar system. Events separated by enormous distances and timescales become linked through gravitational cause and effect. The more astronomers learn about comets, the more they appreciate their role as messengers from deep time. Unlike planets, which have undergone extensive geological evolution, many comets preserve relatively primitive material. They offer rare opportunities to examine matter that has changed little since the solar system's earliest days. In a sense, they allow researchers to look beyond the modern arrangement of planets and glimpse the conditions from which everything emerged. Yet comets are not the only relics from that formative era. Sharing the solar system with them is another population of ancient survivors. These objects are generally rockier, often smaller, and in many cases even more numerous. Scattered across broad regions of space, they preserve additional evidence of planetary construction and ancient collisions. Together they form a vast collection of fragments, each representing a surviving piece of a much older story still written across the architecture of our cosmic neighborhood. 7. Asteroids mapping forgotten chapters of formation. If comets are frozen archives preserving material from the outer reaches of the young solar system, asteroids are the scattered stones of its unfinished construction. They are remnants of a time when planets were still assembling, when countless objects moved through a crowded and turbulent environment shaped by gravity, collisions, and chance. Although asteroids are often portrayed as isolated rocks drifting through space, collectively they represent one of the richest sources of information about how planetary systems form and evolve. Each asteroid carries a fragment of a much larger story, and together they help map chapters of cosmic history that would otherwise remain forgotten. To understand the significance of asteroids, it helps to imagine the solar system during its earliest stages. The young sun had recently formed, surrounded by a vast rotating disk of gas, dust, ice, and rock. Within this disk, particles collided continuously. Some impacts caused material to stick together, producing larger bodies. Those larger bodies attracted additional matter through gravity, gradually growing into planetesimals, the building blocks of planets. This process did not occur smoothly. The environment was crowded, energetic, and unpredictable. Millions upon millions of objects followed intersecting paths. Some merged, others shattered. Certain regions favored growth, while others experienced repeated disruptions. Over time, a handful of bodies became large enough to dominate their surroundings and eventually developed into planets. Yet many smaller objects survived. These survivors are among the asteroids observed today. The majority reside within the asteroid belt, a broad region located between Mars and Jupiter. Early astronomers once speculated that the belt might represent the remains of a destroyed planet. Modern research suggests a different explanation. The material in this region likely never formed a full-sized planet in the first place. Jupiter's enormous gravity repeatedly disturbed the motions of nearby objects, preventing them from combining into a single large world. Instead, countless smaller bodies persisted, preserving a record of conditions present during planetary formation. The asteroid belt is often imagined as densely packed, with rocks crowded together in a hazardous swarm. Popular illustrations sometimes reinforce this impression. In reality, the belt is vast. Individual asteroids are typically separated by enormous distances. A spacecraft can pass through the region without constantly dodging obstacles. Yet despite the emptiness between them, the collective population remains scientifically invaluable. Asteroids vary enormously in size and composition. Some are only a few meters across. Others measure hundreds of kilometers in diameter. Certain asteroids consist largely of metal, while others are rich in carbon compounds or silicate minerals. These differences reflect the diverse environments and processes that existed during the solar system's infancy. In some cases, asteroids appear to be relatively unchanged fragments from the earliest era of formation. Their materials preserve information about temperatures, chemical conditions, and physical processes that existed more than 4 billion years ago. Examining these objects allows scientists to study ancient matter directly, rather than relying solely on theoretical models. Meteorites provide an important connection between asteroids and Earth. Many meteorites are fragments of asteroids that eventually entered our planet's atmosphere. By analyzing these samples in laboratories, researchers can determine their age and composition with remarkable precision. Some meteorites contain minerals that formed before the Earth itself existed. These materials rank among the oldest known objects available for direct study. Within certain meteorites, scientists have discovered tiny grains that predate the formation of the solar system entirely. These microscopic particles originated around ancient stars that lived and died before the Sun was born. Preserved within asteroid material, they survived the collapse of the cloud that formed our solar system. Such discoveries reveal that asteroids do not merely record local history, they preserve traces of events that occurred in earlier generations of stars. The study of asteroids has also revealed that collisions played a central role in shaping planetary systems. Asteroids frequently bear scars from ancient impacts. Some are fragmented remnants of larger bodies shattered long ago. Others belong to asteroid families, groups of objects sharing similar orbits and compositions because they originated from the same parent body. By reconstructing these relationships, astronomers can trace violent events that occurred hundreds of millions or even billions of years in the past. These collisions were not limited to the asteroid belt. Throughout the solar system's early history, impacts occurred on an enormous scale. Young planets experienced frequent bombardment. Craters visible on the Moon, Mercury, and many other worlds provide evidence of this era. Asteroids were among the primary participants in these events, serving both as builders and destroyers. The dual role of asteroids is one of their most interesting characteristics. On one hand, they represent leftover building materials from planetary formation. On the other, they influence the evolution of planets through impacts. A single collision can alter the history of a world. Large impacts affect climates, reshape surfaces, and create entirely new geological environments. Asteroids therefore connect the story of formation with the story of transformation. Not all asteroids remain confined to the main belt. Some occupy regions near Earth. These near-Earth asteroids receive considerable attention because their orbits occasionally bring them close to our planet. Monitoring them helps scientists understand potential impact risks, while also providing opportunities for future exploration. Many of these objects are relatively accessible compared with more distant destinations. Space missions have begun visiting asteroids directly, revealing landscapes far stranger than expected. Some resemble loose collections of rubble barely held together by gravity. Others possess unusual shapes created by past collisions and slow rotation. Surface features include boulders, ridges, craters, and fine dust distributed in ways that challenge earlier assumptions. These observations demonstrate that even small bodies can exhibit surprising complexity. One particularly fascinating discovery is that some asteroids contain water-bearing minerals. Although not covered in oceans, they preserve evidence that water interacted with their materials early in solar system history. This finding supports broader investigations into how water became distributed among planets and smaller bodies. The history of Earth's oceans may be linked, at least in part, to interactions involving ancient asteroids. The more closely researchers examine these objects, the clearer it becomes that asteroids are not mere debris. They are historical records. Their compositions reveal chemical conditions. Their structures preserve evidence of collisions. Their orbits reflect gravitational influences extending across billions of years. Collectively, they provide a map of processes that shaped the solar system long before human beings existed. Yet even as asteroids illuminate forgotten chapters of planetary formation, they point toward deeper mysteries. Their motions, like those of planets and comets, are governed by gravity. For centuries, gravity appeared straightforward, a force capable of explaining celestial movements with remarkable success. But as astronomers expanded their view beyond the solar system and began studying galaxies, clusters, and the larger universe, they encountered phenomena that challenged familiar expectations. The visible matter they could observe no longer seemed sufficient to explain what gravity was doing. Beyond the stars, and beyond the ancient remnants of planetary formation, waited a mystery rooted not in what could be seen, but in what remained hidden. 8. Black holes and the limits of knowing. What are the limits of knowing? The study of asteroids, planets, stars, and galaxies often gives the impression that the universe is gradually revealing its secrets. With better telescopes and more advanced instruments, mysteries that once seemed unreachable become understandable. Yet there are places in the cosmos where knowledge encounters profound boundaries. Among the most remarkable of these are black holes, objects that challenge intuition, reshape space and time, and force science to confront fundamental questions about what can truly be known. Black holes occupy a unique position in astronomy. Unlike stars, they produce no light of their own. Unlike planets, they cannot be observed directly through reflected sunlight. Their presence is inferred through their effects on surrounding matter and on the fabric of space-time itself. In a sense, black holes are discovered through absence as much as through presence. They reveal themselves by influencing what lies nearby. The story begins with gravity. Every object possessing mass exerts a gravitational pull. On Earth, gravity keeps oceans attached to the planet and guides falling objects toward the ground. The Sun's gravity holds the planets in orbit. Throughout the universe, gravity shapes structures large and small, yet gravity becomes especially powerful when enormous amounts of mass are compressed into extremely small regions. Imagine a star much more massive than the Sun. Throughout most of its life, the outward pressure generated by nuclear fusion balances the inward pull of gravity. The star remains stable because these opposing forces exist in equilibrium. Eventually, however, fusion can no longer sustain that balance. The star exhausts its available fuel. Without sufficient outward pressure, gravity gains the advantage. For some stars, the result is a dense remnant known as a white dwarf or a neutron star. For the most massive stars, the collapse continues further. Matter becomes compressed to extraordinary densities. Gravity strengthens dramatically. If enough mass is concentrated within a sufficiently small volume, a black hole forms. One of the most important concepts associated with a black hole is the event horizon. This boundary marks the point beyond which escape becomes impossible. Not even light can travel outward once it passes inside. Because light cannot emerge, the interior remains hidden from direct observation. The event horizon does not necessarily correspond to a solid surface. Instead, it represents a limit within space-time itself. This feature gives black holes much of their mystery. Astronomy traditionally relies on light. Nearly everything known about the universe comes from analyzing electromagnetic radiation in its many forms. When light cannot escape a region, observation encounters a natural barrier. Information from beyond the event horizon becomes inaccessible to outside observers. Yet black holes are not entirely invisible. Matter falling toward them often produces some of the brightest phenomena in the universe. Gas spiraling inward forms an accretion disk, a rotating structure heated to extraordinary temperatures by friction and gravitational forces. As the material accelerates, it emits enormous amounts of radiation. In some cases, powerful jets emerge from regions near the black hole, extending for thousands or even millions of light-years into surrounding space. These energetic displays provide indirect evidence of objects that cannot themselves be seen. Astronomers observe stars orbiting unseen companions. They measure radiation from accretion disks. They track the motion of gas and galaxies. Through these observations, black holes reveal their existence despite remaining hidden at their core. For decades, black holes occupied an unusual position within science. Theoretical calculations suggested they should exist, but direct evidence remained limited. Over time, observations accumulated. Researchers discovered stellar mass black holes formed from collapsing stars. They also uncovered something even more surprising: supermassive black holes residing at the centers of galaxies. These giant objects contain millions or even billions of times the mass of the Sun. The black hole at the center of the Milky Way, known as Sagittarius A*, influences the motions of stars throughout the galactic core. Similar structures appear common across the universe. Many galaxies seem to possess central supermassive black holes that play important roles in their evolution. The existence of such enormous objects raises fascinating questions. How did they grow so large? Did they form gradually through countless mergers and episodes of accretion, or were some born through processes operating in the early universe? Researchers continue investigating these possibilities, and the answers remain incomplete. Perhaps one of the most striking achievements in modern astronomy occurred when scientists obtained the first images associated with black holes. These images did not show the black holes themselves. Instead, they revealed the surrounding glow of matter influenced by extreme gravity. The dark central region corresponded to the shadow created by the event horizon's presence. For the first time, humanity observed a direct visual signature of one of nature's most extraordinary objects. Black holes also transformed our understanding of space and time. According to the theory of relativity, gravity is not merely a force acting across space. Mass and energy influence the geometry of space-time itself. Black holes represent regions where this curvature becomes extreme. Near them, time behaves differently than it does far away. An observer positioned near a black hole would experience time passing normally from their own perspective. Yet someone observing from a great distance would measure that time differently. Clocks in stronger gravitational fields run more slowly relative to clocks in weaker fields. This effect has been confirmed through experiments and observations, though near black holes it becomes dramatically pronounced. Such phenomena challenge ordinary intuition, because human experience evolved in environments where gravitational differences are relatively small. Black holes expose aspects of reality that remain hidden under everyday conditions. They reveal that space and time are more flexible and dynamic than they appear. Yet the deepest mysteries involve questions that remain unresolved. What happens to information that crosses an event horizon? Can the principles of quantum mechanics and gravity be fully reconciled within black holes? Does a complete theory of nature alter our understanding of what lies beyond the horizon? These issues continue to occupy some of the most active areas of theoretical research. The importance of these questions extends beyond black holes themselves. They touch on fundamental principles governing reality. Black holes function almost like laboratories, where the known laws of physics are pushed to their limits. They expose gaps in current understanding and encourage the search for deeper explanations. In this way, black holes embody both achievement and uncertainty. They demonstrate how far scientific inquiry has progressed, while simultaneously reminding us that some mysteries remain unresolved. The universe can be measured, modeled, and explored with remarkable success, yet certain boundaries persist. Knowledge advances, but questions endure. And while black holes represent regions where light cannot escape, elsewhere in the cosmos, immense clouds of gas and dust transform light into something entirely different. Across interstellar space, glowing structures stretch through the darkness, illuminated by nearby stars and shaped by powerful physical processes. These vast formations reveal another side of the universe's story, one in which light paints intricate patterns across the canvas of space itself. 9. Nebulae painting light across interstellar space. After exploring black holes and the regions where light can no longer escape, it is natural to turn towards some of the most luminous structures in the universe. Across the Milky Way and beyond, enormous clouds of gas and dust drift through interstellar space, creating vast formations known as nebulae. These immense structures are among the most visually striking objects ever observed. Yet their beauty is not merely decorative. Nebulae reveal important processes that shape stars, planets, and entire galaxies. They are places where matter gathers, transforms, and interacts with radiation in ways that paint light across the darkness of space. The word nebula originally referred to any fuzzy object in the night sky. Before powerful telescopes existed, astronomers often struggled to distinguish between distant star clusters, galaxies, and true clouds of gas. As observational technology improved, these objects gradually revealed their identities. Some proved to be collections of stars. Others turned out to be entire galaxies beyond the Milky Way. The remaining objects became known as nebulae, immense clouds occupying the spaces between stars. At first glance, interstellar space may seem largely empty. Compared with conditions on Earth, it certainly is. Yet the galaxy contains vast amounts of gas and dust distributed throughout its spiral arms. Much of this material exists at densities far below anything humans normally encounter. Even so, when spread across enormous volumes, it becomes sufficient to form structures spanning dozens or hundreds of light-years. Nebulae appear in several forms, each reflecting different physical processes. Some glow because nearby stars illuminate them. Others shine because radiation energizes the gas within them. Certain nebulae absorb light, creating dark silhouettes against brighter backgrounds. Together, they reveal the complexity of the interstellar medium, the material occupying the spaces between stars. One of the most common types is the emission nebula. These clouds contain gas energized by nearby hot stars. Ultraviolet radiation strips electrons from atoms within the cloud. As those electrons later recombine with atoms, energy is released in the form of visible light. Hydrogen, the most abundant element in the universe, often produces characteristic red and pink hues. The resulting glow can stretch across vast regions, creating some of the most recognizable astronomical images. What appears as a tranquil cloud from a distance is actually a dynamic environment shaped by powerful forces. Radiation streams outward from young stars, stellar winds push against surrounding gas, shock waves travel through the nebula, gravity continues gathering material in certain regions while dispersing it in others. Nebulae are not static paintings suspended in space. They are evolving systems in constant motion. Reflection nebulae provide a different kind of illumination. Instead of glowing through energized gas, they shine by scattering starlight. Tiny dust particles within the cloud reflect and redirect light from nearby stars. Shorter wavelengths scatter more effectively, often giving these nebulae a bluish appearance. The effect resembles certain processes responsible for Earth's blue sky, though it occurs across vastly greater scales. Dark nebulae offer yet another perspective. These clouds are so dense that they block light from stars and glowing gas located behind them. Their shapes become visible through contrast rather than illumination. To observers, they appear as dark lanes or patches winding through brighter regions of space. In reality, these apparent voids are rich reservoirs of material. Many contain the ingredients necessary for future star formation. This relationship between darkness and creation is one of astronomy's recurring themes. Regions that appear empty or obscured often conceal important processes. Dense molecular clouds within dark nebulae serve as stellar nurseries, where new stars gradually emerge. In this way, nebulae connect directly to the story of cosmic renewal. They are not merely remnants of the past, but participants in the ongoing evolution of galaxies. Some nebulae originate through particularly dramatic events. When massive stars approach the ends of their lives, they can release substantial amounts of material into surrounding space. Stellar winds expel gas outward. In later stages, more energetic processes may distribute even larger quantities of matter. The resulting clouds contribute fresh material to the interstellar environment, enriching it with heavier elements produced within stars. This enrichment process is essential to cosmic history. The earliest stars formed primarily from hydrogen and helium. Through nuclear fusion, they created heavier elements such as carbon, oxygen, silicon, and iron. When stars return material to space, these elements become incorporated into future generations of stars and planets. Nebulae therefore function as repositories of cosmic recycling. They collect material from previous stellar generations while providing raw ingredients for those yet to come. Among the most fascinating examples are planetary nebulae. Despite the name, they have little connection to planets. Early astronomers gave them this label because their round appearances resembled planetary disks when viewed through small telescopes. In reality, planetary nebulae form when certain stars shed their outer layers near the ends of their lives. The exposed stellar core remains intensely hot, illuminating the expanding gas around it. Delicate shells, rings, and intricate structures emerge. These formations demonstrate how even relatively ordinary stars can create surprisingly complex patterns through interactions involving radiation, magnetic fields, and stellar winds. The resulting nebulae often persist for tens of thousands of years before gradually dispersing into interstellar space. Observations of nebulae have also transformed humanity's understanding of scale. Some structures extend across distances so vast that light requires years to cross them. Others span hundreds of light years. What appears as a small patch through a telescope may represent a cloud containing enough material to form thousands of stars. The visual delicacy of nebulae can obscure the immense dimensions involved. Modern telescopes observe nebulae across many wavelengths beyond visible light. Infrared instruments reveal stars hidden within dusty clouds. Radio observations trace cold gas distributed throughout the galaxy. X-ray telescopes detect energetic processes occurring in regions influenced by powerful stellar activity. Each wavelength uncovers different layers of information, allowing astronomers to construct increasingly detailed pictures of these complex environments. The study of nebulae highlights an important principle about the universe. Beauty and structure often emerge from interactions among simple ingredients. Hydrogen atoms, dust particles, radiation, and gravity combine to produce formations of extraordinary complexity. No artist directs the process. Physical laws alone generate patterns that appear both intricate and harmonious across enormous scales. Yet nebulae do not exist in isolation. They occupy galaxies, and galaxies themselves are not randomly arranged. As astronomers expanded their observations beyond individual clouds and stars, they discovered that entire galaxies participate in larger structures shaped by forces operating across unimaginable distances. The glowing regions scattered throughout interstellar space are only small components of much grander systems, vast cosmic cities whose organization reveals another layer of order hidden within the universe. 10. Galactic cities organized by invisible forces. Nebulae reveal the beauty of local structures within galaxies, but stepping back from these immense clouds reveals an even larger perspective. Stars, planets, nebulae, black holes, and countless other objects do not exist in isolation. They belong to galaxies, enormous systems containing vast populations of matter organized across astonishing distances. If individual stars can be compared to homes and planetary systems to neighborhoods, then galaxies resemble great cosmic cities. Yet unlike cities built through deliberate planning, galaxies emerge through the action of physical laws operating over billions of years. Their organization reflects the influence of forces that are often invisible but profoundly important. The Milky Way is one such galactic city. From within it, humanity sees only a limited portion of its overall structure. Ancient observers recognized the luminous band stretching across the night sky, but its true nature remained uncertain for centuries. Modern astronomy revealed that this glowing river of light is part of a vast spiral galaxy containing hundreds of billions of stars. Our solar system resides within one of its spiral arms, orbiting the galactic center far from the crowded core. The scale involved is difficult to grasp. Light, traveling at its immense speed, requires roughly 100,000 years to cross the Milky Way from one side to the other. Human civilization occupies only a tiny fraction of that span. Entire chapters of recorded history would pass unnoticed, compared with the timescales governing galactic evolution. Despite their enormous size, galaxies are not random collections of stars. Patterns emerge throughout their structures. Spiral galaxies display elegant arms winding outward from central regions. Elliptical galaxies form smoother, more rounded distributions of stars. Irregular galaxies exhibit shapes that appear less orderly yet still reflect underlying physical processes. These different forms provide clues about how galaxies originate, interact, and change through time. The spiral structure of galaxies is especially fascinating. At first glance, it may seem that spiral arms are permanent collections of specific stars moving together like the blades of a rotating pinwheel. The reality is more subtle. Individual stars travel through the galaxy on their own orbits. The spiral arms function more like regions of increased density, areas where stars and gas become temporarily concentrated. As material moves through these regions, conditions can encourage the formation of new stars, helping maintain the visible pattern. This process resembles certain patterns observed in everyday life. A traffic jam on a highway may move slowly along the road, even though individual vehicles continuously enter and leave it. The pattern persists while its individual components change. Spiral arms behave in a somewhat similar way, maintaining large-scale structure despite the constant motion of their contents. Galaxies are not merely collections of stars. Significant amounts of gas and dust occupy the spaces between them. Massive black holes often reside at their centers. Globular clusters containing hundreds of thousands of stars orbit their outskirts. Streams of stars trace evidence of past interactions. Every galaxy contains layers of structure built through a long history of formation and change. One of the most remarkable discoveries of modern astronomy is that galaxies rarely live alone. They gather into groups and clusters. The Milky Way belongs to a collection known as the Local Group, which includes the Andromeda Galaxy and dozens of smaller galaxies. These systems influence one another through gravity, gradually altering their motions over immense spans of time. The future of the Milky Way itself reflects this interconnected nature. Observations indicate that the Milky Way and Andromeda are moving toward one another. Their eventual encounter will occur billions of years from now. Although individual stars are so widely separated that direct collisions will be unlikely, the galaxies themselves will interact dramatically. Their shapes will change, streams of stars will be redistributed, a new galactic structure will emerge from the merger. Such events are not unusual. Throughout the universe, galaxies collide, merge, and reshape one another. What appears stable over human timescales often proves dynamic when viewed across billions of years. Galactic evolution is an ongoing process, driven by gravity acting patiently across vast distances. Yet gravity alone did not fully explain what astronomers observed. As researchers measured the motions of stars within galaxies, they encountered a puzzle. Stars far from galactic centers moved faster than expected. According to calculations based solely on visible matter, these outer stars should have traveled more slowly. Something seemed to be missing. The discrepancy appeared repeatedly. Not only individual galaxies but entire clusters displayed motions suggesting the presence of additional mass. The visible stars, gas and dust accounted for only part of the gravitational influence being observed. The universe appeared to contain more matter than telescopes could detect. This realization transformed astronomy. For generations, scientists assumed that most of the universe's matter consisted of objects that could be seen directly or indirectly through emitted light. Observations increasingly suggested otherwise. A substantial amount of mass appeared invisible. It neither emitted nor reflected enough light to be detected through conventional means, yet its gravitational effects were unmistakable. This unseen component became known as dark matter. Although its nature remains uncertain, evidence for its existence emerges across many independent observations. Galaxies rotate in ways that imply additional mass. Clusters remain gravitationally bound despite insufficient visible matter. Large-scale cosmic structures appear consistent with the influence of an unseen component helping shape their formation. Dark matter illustrates how invisible forces can organize visible reality. The stars and glowing clouds observed in galaxies may represent only a small fraction of what is actually present. Beneath the luminous architecture lies a hidden framework influencing how galaxies form, grow, and interact. In this sense, galactic cities are built upon foundations that cannot be observed directly. As astronomers expanded their surveys across larger regions of space, another extraordinary pattern emerged. Galaxies were not scattered randomly. Instead, they formed immense networks connected by filaments stretching across hundreds of millions of light-years. Clusters gathered at intersections while vast voids occupied the spaces between them. The universe itself appeared organized on scales far beyond individual galaxies. These discoveries suggested that invisible influences extend throughout the cosmos. The structures observed today may have been shaped by processes operating since the universe's earliest moments. Understanding those processes would require looking beyond galaxies themselves and examining the evolution of the universe as a whole, including a phenomenon so vast that it affects every galaxy, every cluster, and every region of space simultaneously, the ongoing expansion of the cosmos. 11. The quiet expansion stretching cosmic horizons. For much of human history, the universe was imagined as something permanent and unchanging. The stars appeared fixed. The constellations maintained familiar patterns. Night followed day, season followed season, and the sky seemed to provide a stable backdrop against which the events of Earth unfolded. Even after astronomers discovered that stars were distant suns and that galaxies existed beyond the Milky Way, many still assumed that the universe as a whole remained essentially static. It was an understandable assumption. Nothing in ordinary experience suggested that space itself could change. Yet one of the most profound discoveries in modern science revealed exactly that. The universe is not standing still. It is expanding. Distances between galaxies are increasing, and they have been doing so for billions of years. This expansion is not dramatic in the way a storm or explosion appears dramatic. It unfolds quietly, continuously, and on scales so vast that it remained hidden until careful observations uncovered its effects. Nevertheless, it influences the entire cosmos, stretching horizons and shaping the history of everything that exists. The path toward this realization began with the study of distant galaxies. Once astronomers established that many faint patches of light were actually separate galaxies beyond the Milky Way, a new question emerged. How were these galaxies moving? Were they stationary relative to one another, or was something more complex occurring? The answer came through the analysis of light. As discussed earlier, light carries information about motion through a phenomenon known as redshift. When a source moves away from an observer, its wavelengths become stretched, shifting toward the red end of the spectrum. This effect is similar in principle to the change in sound produced by a passing vehicle. As the vehicle moves away, the sound waves become stretched, lowering the perceived pitch. Light behaves in an analogous way. When astronomers measured the spectra of distant galaxies, they discovered something unexpected. Most galaxies exhibited redshifts. More remarkably, the farther away a galaxy appeared, the greater its redshift tended to be. This pattern suggested that distant galaxies were generally moving away from us, and that more distant galaxies were receding more rapidly. At first glance, such observations might seem to imply that Earth occupies a special position at the center of a cosmic expansion. Closer examination revealed a different interpretation. The expansion does not occur from a central point within space. Instead, space itself expands. Every sufficiently distant galaxy observes other galaxies moving away in much the same manner. An analogy often used involves points drawn on the surface of an inflating balloon. As the balloon expands, each point sees all the others moving farther away. No point occupies the center of the surface itself. The expansion arises from the growth of the underlying geometry. Although the universe is more complex than a balloon's surface, the comparison helps illustrate an important idea. Galaxies are generally not racing through space away from a central explosion. Rather, the fabric of space between them is increasing. This distinction fundamentally changed humanity's understanding of the cosmos. The universe became a dynamic system with a history. If galaxies are moving farther apart today than in the distant past, they must have been closer together. Following this logic backward, leads to a time when matter and energy occupied a much denser and hotter state. The implications were extraordinary. The universe was not eternal in its present form. It evolved. Structures developed gradually, galaxies formed, stars ignited, planets emerged. Cosmic history became a story with a beginning, transformation, and ongoing development. Evidence for this expanding universe accumulated through multiple lines of investigation. Measurements of distant galaxies consistently supported the expansion model. Observations of ancient radiation filling space provided additional confirmation. Studies of large-scale cosmic structure further strengthened the picture. Over time, the expanding universe became one of the central foundations of modern cosmology. Yet the expansion introduced new questions. One of the most intriguing concerns the observable universe itself. Because light travels at a finite speed, there is a limit to how far humans can currently see. Light from extremely distant regions may still be traveling toward us. Some areas of the universe lie beyond our present observational reach, simply because their light has not had enough time to arrive since cosmic history began. This creates a cosmic horizon. Much as sailors at sea can only observe a limited portion of the ocean at once, astronomers can observe only a portion of the entire universe. The observable universe represents the region from which light has had sufficient time to reach Earth. Beyond that boundary, additional space may exist, but direct observation remains impossible for now. The concept of a cosmic horizon is humbling. Human knowledge has expanded dramatically, yet there are limits imposed not by technology alone but by the fundamental structure of reality. Even perfect instruments could not instantly reveal regions whose light has not yet arrived. The universe contains boundaries to observation that emerge naturally from the relationship between time, distance, and the speed of light. As researchers examined the expansion more carefully, another surprise emerged. For many years, scientists expected gravity to slow the expansion over time. Galaxies attract one another. Massive structures exert gravitational influence across great distances. It seemed reasonable to assume that the expansion should gradually decelerate as gravity worked against it. Observations revealed something very different. Studies of distant exploding stars indicated that the expansion was not slowing as expected. Instead, it appeared to be accelerating. The universe was not merely expanding. The rate of expansion itself was increasing. This discovery introduced one of the greatest mysteries in modern science. Something seemed to be pushing the universe apart on the largest scales. Whatever this phenomenon was, it appeared to dominate cosmic evolution. Yet its nature remained unknown. Astronomers eventually adopted the term dark energy to describe this mysterious influence. The name reflects ignorance more than understanding. Dark energy is not directly observed in the same way stars or galaxies are observed. Rather, it is inferred from its effects on cosmic expansion. Like dark matter, it represents a component of reality detected through its influence, rather than through emitted light. The existence of dark energy transformed the picture of the cosmos once again. Visible matter, including stars, planets, nebulae, and galaxies, appeared to constitute only a small fraction of the universe's total content. Even dark matter accounted for less than the majority. The largest contribution seemed to come from this mysterious form of energy driving accelerated expansion. As the universe continues stretching its horizons, galaxies gradually move farther apart. Future observers in distant eras may see a very different sky from the one visible today. The long-term consequences of expansion extend across trillions of years, influencing the fate of stars, galaxies, and the cosmos itself. To understand where this immense story may lead, it becomes necessary to explore the hidden components shaping reality and the profound mysteries that still remain concealed within the familiar universe we thought we knew. 12. Mysterious matter hidden within familiar reality. The discovery that the universe is expanding introduced a profound shift in perspective. Space itself was dynamic. Galaxies were not fixed landmarks but participants in an evolving cosmic story. Yet as astronomers measured the motions of galaxies, mapped clusters, and traced the growth of large-scale structure, another realization emerged. The matter visible through telescopes appeared insufficient to explain what the universe was doing. Something hidden seemed to be contributing far more gravity than all the stars, planets, nebulae, and galaxies combined. This conclusion was not reached through a single observation. Rather, it emerged gradually as independent lines of evidence pointed toward the same mystery. Again and again, astronomers encountered situations in which visible matter failed to account for observed motions. The discrepancy appeared in galaxies, clusters of galaxies, and even the largest structures in the cosmos. Whatever was missing seemed to be widespread and influential. The term dark matter was adopted to describe this unseen component. The name can sometimes be misleading. It does not necessarily mean matter that is literally dark in the ordinary sense. A dark object, such as a planet, may still reflect light and eventually become detectable. Dark matter appears different. It neither emits nor absorbs light in ways that current instruments can easily observe. Its existence is inferred primarily through gravity. One of the earliest clues emerged from studies of galactic rotation. Consider the solar system. The planets nearest the Sun move more rapidly in their orbits than the distant planets because the Sun's mass dominates the system. A similar pattern seemed reasonable for galaxies. Most visible stars are concentrated toward galactic centers, so astronomers expected stars in outer regions to orbit more slowly. Observations revealed something surprising. Stars far from galactic centers often moved much faster than expected. Their speeds remained relatively constant across large distances instead of declining significantly. According to calculations based solely on visible matter, many of these stars should have escaped their galaxies altogether. Yet they remained gravitationally bound. The simplest explanation was that galaxies contained far more mass than telescopes could detect. An invisible halo of matter appeared to surround them, extending well beyond the regions occupied by most visible stars. This hidden mass provided the additional gravity needed to explain the observed motions. Similar evidence emerged from galaxy clusters. Clusters are among the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. When astronomers measured the motions of galaxies within these clusters, they found that visible matter again seemed insufficient. The galaxies moved too rapidly to remain bound if only observable material were present. Additional unseen mass appeared necessary. Over time, further observations strengthened the case. Gravitational lensing provided particularly compelling evidence. According to the theory of relativity, mass bends space-time, and light follows those curved paths. As a result, massive objects can act like cosmic lenses, distorting and magnifying the appearance of more distant sources. By studying these distortions, astronomers can estimate the total mass present in a region. Repeatedly, gravitational lensing measurements indicated more mass than visible matter alone could account for. The invisible component seemed real, not merely a flaw in calculations or observations. One of the most remarkable aspects of dark matter is how familiar reality can conceal it. Human beings experience the universe primarily through light. Vision depends on light. Telescopes depend on light. Much of astronomy relies on interpreting electromagnetic radiation across different wavelengths. Dark matter reminds us that visible phenomena may represent only a fraction of what exists. Imagine entering a vast city at night and seeing only illuminated windows while everything else remains hidden. The visible lights would reveal some information, but much of the city's structure would remain concealed. In a similar way, stars and glowing gas may represent only the luminous highlights of a much larger cosmic framework. Current evidence suggests that dark matter played an essential role in shaping the universe. Shortly after the universe's earliest stages, matter began gathering under gravity. Regions containing slightly more mass attracted additional material, gradually growing into larger structures. Dark matter appears to have contributed significantly to this process, helping create the gravitational scaffolding upon which galaxies later formed. Without such a framework, the universe might look very different today. Galaxies may have formed more slowly, or perhaps not in the same way at all. The cosmic web observed across immense distances appears consistent with models in which dark matter influences the growth of structure from the earliest epochs onward. Yet, despite its apparent importance, the true nature of dark matter remains unknown. Scientists know what it does far better than what it is. This distinction is important. Gravity reveals its presence, but identifying the particles or phenomena responsible has proven extraordinarily challenging. Many possibilities have been proposed. Some theories suggest entirely new particles, unlike those currently included in the standard understanding of matter. Others explore modifications to existing ideas about gravity. Researchers conduct experiments deep underground, operate sensitive detectors, and analyze astronomical observations in search of clues. So far, however, definitive answers remain elusive. This situation illustrates an important feature of science. Progress does not eliminate mystery. In many cases, new discoveries reveal deeper questions. Dark matter emerged not because scientists lacked data, but because they collected enough data to recognize that existing explanations were incomplete. Knowledge expanded, and with it came awareness of previously hidden uncertainty. The mystery becomes even more intriguing when considering proportions. Visible matter, everything directly observed in stars, planets, gas, dust, and living organisms, appears to represent only a small fraction of the universe's total content. The familiar reality experienced every day may be a minor component of a much larger whole. This realization carries a certain philosophical weight. Human perception evolved to navigate local environments on a planetary surface. Our senses were not designed to reveal the full structure of the cosmos. Scientific instruments extend those senses, allowing deeper exploration, yet the universe continues to reveal layers beyond immediate experience. The familiar may not be fundamental. What appears obvious may be only a surface manifestation of deeper processes. Dark matter also highlights the interconnected nature of cosmic investigation. Its existence becomes apparent only when observations are combined across many scales. The motions of stars, the behavior of galaxies, the structure of clusters, and the evolution of the universe all contribute pieces to the puzzle. No single observation provides the entire answer. Understanding emerges through the convergence of evidence gathered from many directions. Perhaps the most remarkable aspect of the mystery is its persistence. Decades of research have refined measurements and strengthened the evidence, yet the identity of dark matter remains unresolved. It stands as one of the clearest examples of how much remains unknown despite centuries of scientific progress. And while dark matter challenges our understanding of what the universe contains, another mystery challenges our understanding of reality itself. In regions where gravity becomes extreme, the flow of time no longer behaves in ways that align with ordinary intuition. Clocks can tick at different rates. Distances and durations become intertwined. To explore these strange effects is to enter one of the most fascinating territories in all of science, where the familiar experience of time begins to reveal a far deeper nature. 13. Time's strange behavior near extreme environments. Time feels simple because human beings experience it continuously. Seconds become minutes, minutes become hours, and days unfold in a steady sequence that appears universal. A clock on one wall agrees with a clock on another. Morning arrives, afternoon follows, and night eventually returns. This regularity creates the impression that time flows identically everywhere. For most everyday purposes, that assumption works remarkably well. Yet the deeper scientists investigated the universe, the more they discovered that time is not as fixed or uniform as it seems. In extreme environments, particularly those involving immense gravity or extraordinary speeds, time behaves in ways that challenge ordinary intuition. For centuries, time was often regarded as an independent backdrop against which events occurred. Space provided the stage, and time provided the schedule. Both seemed absolute. Whether a person stood on Earth, traveled across an ocean, or observed the stars, time itself was assumed to proceed identically for everyone. This view changed dramatically during the 20th century through the work of Albert Einstein. His theories revealed that space and time are not separate entities, but interconnected aspects of a larger structure known as space-time. More surprisingly, Measurements of time can depend upon motion and gravity. The passage of time is not completely universal. Under certain conditions, different observers can experience different amounts of time between the same events. The idea initially seems strange because the effects are usually too small to notice in daily life. Human beings move relatively slowly compared with the speed of light, and Earth's gravity, while substantial, is modest compared with the most extreme environments in the universe. Yet when conditions become extraordinary, the differences become measurable and sometimes dramatic. One way time changes involves motion itself. According to relativity, an observer moving at very high speed relative to another observer experiences time differently. As velocity increases, time for the moving observer progresses more slowly compared with someone at rest relative to them. This phenomenon is known as time dilation. The effect is not a trick of perception or a flaw in measurement. It is a genuine feature of reality confirmed through experiments. Highly accurate clocks transported aboard aircraft, satellites, and spacecraft show tiny but measurable differences when compared with clocks that remain on Earth. Particles created in laboratories also behave exactly as relativity predicts, surviving longer when traveling at high speeds than they would if stationary. The reason such effects remain unnoticed in ordinary life is that everyday velocities are extremely small compared with the speed of light. A passenger jet moves quickly by human standards, but its speed remains insignificant compared with light's immense velocity. Only under extreme conditions do relativistic effects become substantial enough to transform the experience of time in obvious ways. Imagine a spacecraft capable of traveling at a significant fraction of the speed of light. To those aboard, time would seem normal. Clocks would tick normally. Conversations would proceed naturally. Yet observers remaining on Earth would measure time differently. Upon returning from such a journey, travelers might discover that more time had passed on Earth than they personally experienced. This possibility is one of the most fascinating consequences of relativity. The future is not reached through mysterious machines or speculative technology. In a limited sense, time travel toward the future is built into the structure of space-time itself. Moving through extreme conditions can alter how much time an observer experiences relative to others. Gravity introduces another form of time dilation. Earlier explorations of black holes revealed that gravity influences space-time. This influence affects not only motion through space but also the passage of time. Clocks located in stronger gravitational fields run more slowly relative to clocks in weaker gravitational fields. Again, this is not merely theoretical. The effect has been measured repeatedly. Modern navigation systems such as GPS must account for relativistic differences between clocks on satellites and clocks on Earth's surface. Without these corrections, positioning errors would accumulate rapidly. Technologies used every day depend upon the reality of relativistic time. Near massive objects, the effect becomes increasingly pronounced. A clock positioned close to a dense neutron star would run more slowly than one far away. Near a black hole, the differences become extraordinary. An observer watching from a safe distance would see processes near the event horizon unfolding more slowly. Time itself appears stretched by the immense curvature of space-time. These effects challenge common assumptions because human intuition developed under conditions where time behaves almost uniformly. Evolution provided no reason to anticipate relativistic physics. The universe, however, operates according to principles far broader than those encountered during everyday experience. One of the most profound consequences of relativity is the realization that time cannot be fully separated from space. Distances and durations become intertwined. Events that seem simultaneous from one perspective may not appear simultaneous from another. The ordering of certain events can depend upon an observer's state of motion. This does not mean reality becomes arbitrary. Relativity preserves consistent physical laws for all observers. Yet it reveals that concepts once assumed absolute are more flexible than previously imagined. Space and time adapt to circumstances, responding to motion, gravity, and geometry. The strange behavior of time becomes especially important when studying the universe as a whole. Light from distant galaxies has traveled for billions of years. Black holes distort space-time, Rapidly moving particles cross interstellar distances. Understanding these phenomena requires acknowledging that time is an active participant in cosmic processes rather than a passive background. Even the history of the universe itself reflects this relationship. The expansion of space influences how light travels across immense distances. Ancient radiation reaching Earth today carries information from epochs billions of years in the past. Astronomy constantly links observations of space with observations of time. Looking outward means looking backward. Some of the most intriguing unanswered questions in physics involve the nature of time itself. Why does time appear to move in a single direction? Why do memories point toward the past rather than the future? How does time emerge from the deeper laws governing reality? These questions remain active areas of investigation, connecting cosmology, quantum mechanics, and fundamental physics. Scientists have made remarkable progress in understanding how time behaves, yet its deepest nature remains elusive. Like dark matter and dark energy, time reveals that reality possesses layers extending beyond immediate experience. The familiar flow of seconds and hours may represent only a local expression of principles operating on far grander scales. Perhaps that is one of the universe's most enduring lessons. The closer we examine reality, the more we discover that ordinary appearances conceal extraordinary depths. Time seems simple until gravity bends it. Space seems empty until hidden structures emerge. Matter seems familiar until most of it becomes invisible. Again and again, the cosmos reveals that what appears straightforward often rests upon foundations far stranger than first imagined. And as astronomers continue studying expansion, gravity, matter, and time, a final question naturally arises. If the universe has a history, if it changes and evolves, then what future awaits it? The answer lies not only in the stars visible today, but in the immense processes already shaping the destiny of the cosmos across trillions of years yet to come. 14. The universe's future, written in motion. Every chapter of cosmic history is shaped by motion. Planets orbit stars. Stars circle galactic centers. Galaxies drift through expanding space. Light travels across billions of years before reaching distant observers. Nothing in the universe remains completely still. Motion is woven into the fabric of reality itself, and because the universe continues to move and evolve, it also possesses a future. Although no one can observe that future directly, the laws of physics allow astronomers to explore possible outcomes. By studying gravity, stellar evolution, galactic interactions, and cosmic expansion, scientists can trace the broad directions in which the universe appears to be heading. The future begins with processes already underway today. The Sun, like every star, is gradually transforming hydrogen into helium within its core. This process releases energy and allows the Sun to shine, yet the supply of hydrogen available for fusion is finite. The Sun is stable because nuclear reactions and gravity remain in balance, but that balance will not last forever. Fortunately, these changes occur on timescales far beyond human civilization. The Sun is approximately halfway through its main lifetime. Billions of years remain before major transformations begin. Long before then, countless generations will have lived and vanished beneath its light. From a cosmic perspective, however, stellar evolution is inevitable. Stars are not permanent objects, they are processes. As the Sun ages, its luminosity will gradually increase. Conditions on Earth will change accordingly. Eventually, the planet may become unable to support the environments familiar today. Far in the future, the Sun will expand into a red giant, transforming the inner solar system. Its outer layers will extend outward, and the architecture of nearby planetary orbits may be altered dramatically. This destiny is not unique to our star. Similar processes occur throughout the galaxy. Every star follows an evolutionary path determined largely by its mass. Massive stars burn brightly but briefly. Smaller stars consume their fuel more slowly. Some red dwarf stars may continue shining for trillions of years, far longer than the current age of the universe. Because stars have different lifetimes, the galaxy's future unfolds gradually rather than through sudden change. New stars continue forming in certain regions, while older stars reach the ends of their lives elsewhere. The Milky Way remains a dynamic system in which creation and transformation occur simultaneously. Yet the supply of raw material is not unlimited. Star formation depends on the availability of gas and dust. Over immense spans of time, galaxies consume much of this material. Some is locked into long-lived stars, some is expelled into intergalactic space. As the ages pass, the rate of star formation is expected to decline. The future night sky of a distant civilization might therefore look different from the one visible today. Regions currently rich with stellar nurseries may become quieter. Brilliant young stars may become less common. The galaxy would not suddenly grow dark, but its character would slowly change as available resources diminish. While stars evolve, galaxies continue their own journeys. Earlier, we explored the approaching encounter between the Milky Way and the Andromeda Galaxy. This event remains one of the most significant future developments in our local cosmic neighborhood. Billions of years from now, the two galaxies are expected to interact and eventually merge. From a distance, the process would appear spectacular. Spiral structures would become distorted. Vast streams of stars would arc through space. Gas clouds would compress, potentially triggering episodes of enhanced star formation. Over time, the two systems would settle into a new configuration, creating a larger galaxy with a different shape and structure. Such mergers are common throughout cosmic history. The universe continually reshapes itself through gravitational interactions. Galaxies grow not only by forming stars internally but also by combining with one another. The future Milky Way is therefore not simply an older version of the present galaxy. It is likely to become something fundamentally different. Beyond local events lies the influence of cosmic expansion. The expansion of the universe affects the largest scales of reality. Galaxies within gravitationally bound groups may remain connected, but more distant galaxies continue moving away as space expands. Over immense periods, the observable universe changes. A civilization existing trillions of years in the future might observe far fewer galaxies than astronomers see today. Many distant systems would have moved beyond observational reach. Their light would become increasingly stretched and faint. The vast cosmic web visible now would gradually disappear from view, leaving local gravitationally bound structures as the dominant visible features. This possibility carries an intriguing implication. Present-day humanity occupies a fortunate period for cosmology. The universe is old enough for complex structures to exist, yet young enough that evidence of large-scale cosmic history remains observable. Future observers may find it much more difficult to reconstruct the universe's origins because key evidence will have faded beyond detection. The ultimate fate of the universe depends significantly on the nature of dark energy, the mysterious phenomenon associated with accelerated expansion. Current observations suggest that expansion will continue and perhaps dominate cosmic evolution indefinitely. If this picture remains correct, galaxies not bound together by gravity will continue separating. Over unimaginably long timescales, stars will gradually exhaust their fuel. New star formation will decline. Existing stellar populations will age. White dwarfs, neutron stars, and black holes will become increasingly common remnants of earlier generations. The universe would enter a much quieter era than the one experienced today. This possible future is often described as the heat death of the universe, though the term can be misleading. It does not refer to intense heat. Rather, it describes a state in which energy becomes increasingly dispersed and organized activity becomes more difficult. Differences in temperature and concentration that drive physical processes gradually diminish. Yet even this distant future unfolds over timescales almost impossible to comprehend. Trillions, quadrillions, and vastly larger numbers of years separate the present from such conditions. Compared with these durations, the entire history of human civilization occupies a fraction so small that it nearly disappears. Black holes themselves participate in this long-term evolution. Once thought eternal, theoretical work suggests that black holes may slowly lose energy through processes associated with quantum physics. Over incomprehensibly long periods, even these extreme objects could eventually disappear. The universe's future extends so far beyond ordinary experience that familiar categories struggle to describe it. What makes these possibilities remarkable is not merely their scale, but their connection to present observations. The future is written in motion already occurring. Every orbit, every expansion, every transformation contributes to larger patterns unfolding across cosmic time. The universe carries its history forward through the laws governing matter, energy, space, and time. And as we follow those motions toward the farthest horizons imaginable, a final perspective begins to emerge. The stars, galaxies, black holes, nebulae, planets, and hidden structures explored throughout this journey are not isolated wonders. Together they form parts of a single vast story, one that stretches from the earliest moments of cosmic history to futures beyond easy comprehension. In that larger view lies perhaps the deepest wonder of all. 15. 100 wonders within a boundless cosmos. The universe invites a particular kind of reflection, not because it offers simple answers, but because it reveals an endless sequence of connections. Every discovery seems to lead naturally to another question. Every structure points toward a larger structure. Every explanation opens the door to deeper mysteries. Across this journey through 100 wonders, we have moved from darkness to starlight, from planetary systems to galaxies, from hidden matter to the future of the cosmos itself. What emerges is not a collection of isolated facts, but a portrait of a universe woven together by patterns that span unimaginable distances and timescales. One of the most remarkable aspects of this portrait is the role of scale. Human beings live on a single planet orbiting a single star within one galaxy among countless others. Measured against cosmic dimensions, that position appears small, yet the ability to understand even part of the larger picture represents something extraordinary. The atoms that compose human brains were forged in ancient stars. The laws that govern galaxies also govern the motions of particles within our bodies. In this sense, the observer and the observed belong to the same story. Throughout history, people have looked upward and wondered what lay beyond immediate experience. The earliest sky watchers could not know about black holes, dark matter, exoplanets, or expanding space, yet they recognized something that remains true today. The night sky inspires curiosity. It encourages questions that extend beyond daily concerns. It reminds us that reality is larger than the horizon visible from any one place. Consider how many layers of structure exist simultaneously within the universe. A single grain of cosmic dust may drift through a nebula. That nebula may occupy a spiral arm of a galaxy. The galaxy may belong to a cluster. The cluster may sit within a filament of the cosmic web. Each level influences and connects to the others. No structure exists entirely alone. Relationships extend outward in every direction. This interconnectedness appears again and again throughout astronomy. Stars create the elements needed for planets. Planets emerge from materials surrounding young stars. Moons influence planetary environments. Comets and asteroids preserve records of earlier eras. Galaxies recycle matter through successive generations of stellar birth and death. Even the largest structures in the universe trace their origins to conditions present in the earliest moments of cosmic history. Such continuity gives the cosmos a sense of coherence. The universe is not merely a collection of objects scattered through space. It is a process. Matter changes form, energy flows between systems, structures emerge, evolve, and transform. The story never remains fixed. Motion and change are fundamental characteristics of reality. At the same time, the universe demonstrates remarkable stability. Physical laws appear consistent across enormous distances. The same principles governing gravity on Earth influence the motions of galaxies billions of light-years away. The same atomic processes observed in laboratories occur within distant stars. This consistency allows scientific understanding to extend far beyond direct experience. Perhaps one of the most profound lessons revealed by astronomy is the relationship between knowledge and mystery. Every generation inherits questions from the previous one. Some mysteries are resolved, others deepen. The discovery of galaxies answered certain questions about the nature of the Milky Way, while creating new questions about the structure of the universe. The discovery of dark matter explained puzzling observations while introducing an entirely new mystery about the composition of reality. This pattern is not a sign of failure. It is evidence of progress. Expanding knowledge often reveals previously invisible frontiers. The horizon moves outward. What was once unknown becomes understood, while new regions of uncertainty emerge beyond it. The universe itself encourages this process because it contains far more than can be explored in a single lifetime. Even within our own galaxy, hundreds of billions of stars await investigation. Across the observable universe, the number of galaxies likely reaches into the hundreds of billions as well. Around many of those stars orbit planets. Around many of those planets unfold histories entirely unknown to us. Some worlds may be barren and silent. Others may possess oceans, atmospheres, or environments unlike anything found in the solar system. The sheer diversity implied by these possibilities expands the imagination. Reality appears richer than earlier generations could easily have envisioned. Yet perhaps the most striking wonder is not any specific object or phenomenon. It is the existence of a universe capable of producing complexity at all. From simple beginnings emerged stars, galaxies, planets, chemistry, biology, consciousness, and curiosity. The same cosmic processes that formed nebulae and black holes eventually produced beings able to contemplate those phenomena. This does not make humanity the center of the universe. Astronomy has repeatedly demonstrated that no privileged physical center exists. Instead, it reveals something different. Understanding itself becomes part of the cosmic story. The universe developed structures capable of examining the universe. There is a quiet elegance in that realization. Ancient starlight travels across billions of years before reaching a telescope. Hidden matter shapes galaxies. Time bends near extreme gravitational fields. Expansion stretches the fabric of space itself. And within a small corner of one galaxy, observers piece together these patterns using mathematics, observation, and imagination. The cosmos remains far from fully understood. Dark matter has not revealed its identity. Dark energy remains mysterious. Questions surrounding black holes, quantum gravity, and the earliest moments of cosmic history continue to challenge researchers. Entire categories of phenomena may still await discovery. Future generations will almost certainly inherit a picture of the universe richer than the one available today. That prospect is not unsettling, it is inspiring. A fully solved universe might eventually become predictable and finite in intellectual scope. A universe containing unanswered questions remains open. It invites exploration. It rewards curiosity. It continually expands the boundaries of understanding. As we reach the end of this journey through 100 sleepy wonders of the universe, the night sky appears both familiar and transformed. The stars remain where they always seem to be, yet behind their quiet light lie stories stretching across billions of years. Darkness conceals hidden structures. Galaxies drift through expanding space. Ancient photons continue arriving from remote corners of time. Invisible matter shapes visible reality. The future unfolds through motions already underway. The cosmos offers no final chapter in the ordinary sense. Every ending becomes the beginning of another question. Every horizon reveals a more distant one beyond it. The universe remains vast, evolving, and unfinished, and perhaps that is the deepest wonder of all. Not that the cosmos contains countless mysteries, but that after everything we have learned, it still possesses room for infinitely more.